Um, okay, I haven't streamed for a while now, but I'm gonna try to get a couple more streams, a couple more sessions in the next days, so we can push and move a bit forward. But what I've been doing recently, so I've been working on kind of going back from what I was reading here in the quantum formalism part, sort of to find an anchor to kind of start digging a bit more deep around the and trying to understand at least everything here, right? So last session I did take a look at the definitions of what the action really means, and I so I think that helped a lot. I did also dive into the after taking a look at where does this lead me. I ended up with Lagrangian mechanics, and I did take a look at some of these videos, right? So, but so this is the video that I liked the most. Although it did help the fact that I was, looking up at some of the stuff up in the Wikipedia in terms of the Lagrangian being the action. And I wanted to try to do a bit more first principles thinking today in terms of um, around the action concept, right? And I think I get the general concept of Lagrangian mechanics, and it's really the wait a second, is this the one that I looked at? I think that's the one I looked at.
Brauchst du einen Laptop, den du nicht ständig laden musst? Zeit zu wechseln. Zu einem Chromebook mit bis zu 12 Stunden Akkulaufzeit. Oder wie wär's mit automatischen Updates
And it's
ohne
probably
Nerven?
too loud.
Okay, I am going to
So
show
why I
the whole
can't
idea
hear
behind
it,
Lagrangian
I
mechanics.
really don't
And so
know.
this is an example. This ball rolling on this track would be something that would be
Because
similar
that
to
makes
what
it
you would
difficult
use
for
in
me.
a trivial problem. Okay, that one. And
But this was a good
basic
video that kind of motivates
for
the
quantum
idea.
Then
It
Lagrangian
doesn't dig
mechanics
too
says that
much
if you
into
calculate the Lagrangian,
why
then
this
the
makes
path of
sense
the
and
ball
whatnot.
up
It's
into
more like
action
that's the tool,
is
and
the
that's
same as the
how
point on the
that's how you
left
want to go
is
about
A,
it. So I
where
actually really recommend the
what
video.
defines the function
Didn't know about
that
the channel before.
minimizes
Probably
the
subscribe.
integral, then you would
But
have to use the order in flat space and then find the Lagrangian t minus u. From that, we'll use the Euler-Lagrangian in generic
let me see.
coordinates, the Lagrangian problems. First, that motion of the ball.
That is essentially it, right? So
Okay, I'm going to do this for two problems. And we're going to work this
then
through.
you got to get
Start off
these,
with
and then you
two
can try to
simple
find the
problems.
stuff that you're trying to
The
find. Classically
t
speaking,
minus
that is
u,
just classical
1/2
mechanics,
m
right?
y dot squared
Um,
minus mgy.
Now
Now
the general so the general idea is that you have this action concept, right? And um, what Lagrangian mechanics is trying to tell you is take this action and find the evolution, right? Like it's a bit confusing. They call it path, but I guess it's just because a lot of examples are just tied to actual movement in space, right? But like find the evolution that minimizes the action. I don't know if the principle of least action comes from experimental data or not. Maybe that's something to take a look at. Principle of least action. But that's the idea, right? Stationary action principle. And now I guess the action is then defined differently depending on the context. So the way that I understand the Lagrangian in Lagrangian mechanics classically is kind of taking the assumption that the Lagrangian is a good action, it's a good definition of an action in this particular case. And so it's the kinetic energy minus the potential energy. Why? What I'm trying to understand is why does this make sense at all, right? Because, okay, I get it that these two types of energies, they probably define, like, it's all you need to know about the system, right? So you have the energy that it's associated to the movement. I think that's a way to think about the kinetic energy. So to the velocity that it currently has. And the potential energy is the energy that is, potentially usable, right? Be it like because of it, whatever the position and the gravitational force or whatever the right name is, you have that potential energy, right? Or if it's like a spring, then sort of the spring, when it's like contracted or expanded, that it's got some potential energy in there, because you're always looking at a frozen moment in time. But why minus, right? It makes sense, I think, backwards. If you think about it backwards, it makes sense because you're trying to define the action in a way that you're trying to solve the problem from a sort of trying to find the path that minimizes the action. And so that is something that, yeah, I mean, what would be the way to evolve a system such that that Lagrangian is minimal? Well, the potential energy it's got a negative sign. So ideally, the minimal of this of the lower bound of these would be you have no kinetic energy, and all your energy is potential. So that literally means you're not moving, right? You have no kinetic energy. You're just stationary, and I think that is so. This is something that I ended up connecting in between, you know, thoughts and flying thoughts and whatnot in the past days. But the stationary action principle, also known as the principle of least action, is a variational principle that, when applied to the action of a mechanical system, yields the equations of motion. The principle states that the trajectories are stationary points, critical points of the system's action functional. Okay. The term least action is a historical misnomer, since the principle has no minimality requirement. The value of the action functional need not be minimal. Okay. The principle can be used to derive Newtonian, Lagrangian, and Hamiltonian equations of motions, and in general relativity. In relativity, a different action must be minimized or maximized. Okay. In classical mechanics, and electromagnetic expressions are a consequence of quantum mechanics. The stationary action method helped in the development of quantum mechanics. Blah, 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 blah. So Dirac demonstrated how the principle can be used in quantum calculations by discerning the quantum mechanical underpinning of the principle in quantum interference and alpha amplitudes. It remains a central model, but what does this stationary principle say? A general statement. So the starting point is the action, denoted S, of a physical system. It is defined as the integral of the Lagrangian between two instants of time. Technically, okay, so the action is actually defined as the integral of the Lagrangian. Okay. And the Lagrangian is telling you, the Lagrangian is a number that quantifies what? So the Lagrangian is, the action is not the Lagrangian, the action is the integral of the Lagrangian. And the Lagrangian is, it quantifies it's a function. So the Lagrangian is a function in this case. Give me a second. Oh, now, yeah, cool. So what the Lagrangian is, the action is the integral. The Lagrangian is a function, and it's a function that tells you in every point in time. It's a time-dependent function. It's telling you. It almost feels like the Lagrangian of itself has no meaning as a number. It's only got a meaning when you embed it into the concept of an action, right? To say it's a number that if I integrate across this function, it gives me a sense of how much the systems change over time. And so I think that's the best I can do, to be honest. And so by convention, so it's a convention, right? So it's T minus V, or this kinetic and potential energy. The reason it's minus is because, and it feels like the reason it's minus is just because of that, right? Because you're designing the function so that it gives you the right type of answer. You're telling you want this function to be at its minimum whenever the potential energy is the only energy that's in the system, and the other way around, you want it to be at its maximum when all the energy is kinetic energy. This means, I don't know what it means. It just means, I guess, you're moving as fast as you can. I don't know. And I guess that you could think of other energies, but maybe there's an assumption out there where the system is somewhat isolated or whatnot. But I think that is, I can't, maybe I'll come back to this at some point, but I think that is basically a good summary of what I've done in the past couple of days, right? So I was really kind of struggling a bit to try to connect these two things, but it feels like it's a bit of a chicken and egg problem. I was trying to understand what the Lagrangian per se means, because it felt pretty arbitrary. But then, like, if you take a look at the formulation or the whole T minus V thing, it makes sense only when you embed it into the action concept, right? And say, yeah, because that's the type of function you want. You want a function that is minimal, so that it satisfies the stationary action principle. But what does it say here? So, and now let's try to walk upwards. And maybe I should do some of these. I should do maybe some exercises. Maybe I should plan some like working sessions in the near future where we would actually go and do some of these exercises, or like to kind of like calculate stuff with the Lagrangian. It's defined. So the action is defined as the integral of the Lagrangian between two instants of time, technically a functional of the. So what is the functional? Like, I keep coming across these. Functional has at least three meanings. And modeling algebra refers to a linear mapping from a vector space into its field of scalars. A linear mapping from a vector space into its field of scalars. And I don't know what it means, but more generally, historically refers to mapping from space X into the real numbers or complex numbers. In computer science, it's a higher order. It's higher order functions. So functions that take functions as arguments or return them. Okay, so it's like a. Is that the way that these? Because here it says the Lagrangian is a functional. Of the n generalized coordinates q, which are functions. Okay, yeah, so that's the definition, right? So that it is a function that takes functions. So of the n generalized coordinates, which are functions of time and define the configuration of a system. Okay, so okay, so this is a more general definition. So Lagrangian, is it this referring to the action or to the Lagrangian? I think it's referring to the action. So the action is the functional. Yeah. Which are functions of time and define the configuration of a system. The dot denotes the time derivative and t is time. Mathematically, the principle is that delta, the differential of s equals 0. Yeah, so that's what I'm saying. So a small change. It's so awkward, like it's so awkward how things are so formal and then it's like, that means a small change. The path taken by the system between times t1 and t2 and configurations q1 and q2 is the one of which the action is stationary, no change to first order. Stationary action is not always a minimum, despite the historical name, at least of least action. It is a minimum principle for sufficiently short, finite segments of the path. In applications, the statement and definition of action are taken together. So what it's saying is that, yeah, it's not that the change is minimal, but like the small changes within the path are minimal. So the action and Lagrangian both contain the dynamics of the system for all times. The term path simply refers to a curve traced out by the system in terms of the coordinates of the configuration space. The curve, yeah. And I guess the configuration space technically means it's a configuration of a system. In classical mechanics, the parameters that define the configuration of a system are called generalized coordinates in the vector space. So I guess the configuration is whatever defines the system state, right? Whether like be it the energies or be it whatever. So in this case, or in the typical case, you would say that Q is a position in space, say three-dimensional space, and then the configuration is the actual energies you're using, right? So say, the whatever kinetic, and that's how you're tracking the configuration of the system, I guess. And the vector space defined by these coordinates is called configuration space. Generalized coordinates. Parameters that describe the configuration of a system relative to some reference configuration. These parameters must uniquely define the configuration of a system relative to the reference configuration. This is then assuming that this can be done with a single chart. The generalized velocities are the time derivatives of generalized coordinates. That's already, I think, just one level of abstraction upper. But okay, I think we're good with these. Now let's try to go a bit one step forward just to make sure we're always moving towards our goal, which is, let's reread this section a little bit. Because that the turns, and I almost forgot. Consider a path in the multi-way system going through multi-way space to know how much. And I'm really just gonna try now and probe whether I've gone deep enough so I can understand fill up some of the gaps that I had when I was reading these. Because then before I decide to invest a bit more into the path integral formalism, which that's probably what I want to do next, right? And I know I should probably invest more time on these, but it doesn't feel like it's good. Like I could do some of and I probably should do some of the exercises, but I don't know if it's so much of a smart investment at this point in time, especially because I want to focus on the quantum mechanical stuff. Like, I mean, it's like, yeah, it's just details, right? I guess the way you solve these things is just partial differential equations or differential equations, which is a topic that I've also never touched before. And at some point I should just face this. But I understand what the Lagrangian mechanics concept and framework is talking about. So let's see if we can jump straight to the path integral stuff. because it's the quantum stuff that I'm interested in. It's like if I had time to do everything, I'd like to, of course, do everything, but I don't have time to do everything. But now consider the path in the multi-way system going through multi-way space. To know how much turning to expect in the path, we need in effect to integrate the Lagrangian density along the path together with the appropriate volume element. And this will give us something of the form. Okay, let's try to understand where are they taking that from. So S is the action. And let's go a bit back. This is the turning. When do they talk about the turning first? Here. So now note that every node in the multi-way causal graph represents some event in the multi-way graph, but events are what produce branching and turns of paths in the multi-way graph. So what this suggests is that the amount of turning of a path in the multi-way graph should be proportional to the energy multiplied by the number of steps. Let's try to process these. Why? How do you bring in energy in here, right? So energy in its most essential definition is just the capacity to do. It's the capacity to do work, right? I've been doing some of my basics homework here. What is energy? What is energy? Yeah, physical mental activity. No, but I mean, it is like that, right? Energy, the ability to do work, which is the ability to exert a force. So energy is like what allows you or an object not to just stay stationary, right? So if you've got potential energy, that's the energy that you can potentially use to actually do work. So how does this come in here in the model? So what it suggests is the amount of turning is proportional to the energy multiplied by the number of steps. Let's put that aside for a second. I don't know why you multiply that by number of steps, unless that is okay, yeah, because I guess what this is saying is that, if you're at a certain point in the graph and you have a certain angle in terms of turning, like that actually depends on the previous steps, right? Because you might have been turning before. So the fact that now you can have like so the fact you can now have a bit of a bigger angle is both dependent on on the angle you're coming from, and yeah, kind of the energy, which I think this is maybe the way this is mapped is like the capacity of the amount of rules you could apply to a state somewhat relate to energy. I mean, you could map the concepts, right? Because so if I am at a terminal state, this means that no rule can be applied to me as a node. Then I have no potential energy. Maybe that could be a way to connect things. Whereas if all the rules can apply to me, I have a lot of potential energy. And that means I can fork into a lot of paths. That in and of itself is not connected to the steps. What's connected to the steps is that angle, but I don't know how that angle is defined. So let's go one step back here. You know what? Maybe let's scan quickly the whole thing. So entanglement stays. This is still not super clear how the entanglement is defined here, but the fact that entanglement is, I'm not so much. That's not so much clear to me that entanglement is basically a reflection of common ancestry. But anyway, that's specifics of the model. Consider the following multi-way graph as transition system. Each branching graphs considered to be entangled. Given a particular affiliation with the multi-way graph, we can now capture the entanglement of states as this affiliation for this transition system. In general terms, we expect states are closed in a branchial graph. Yeah, that's not supposed to be the same like a geometry of ordinary space. For example, it will not typically correspond to a finite dimensional manifold. We can still think of the space as some kind that is reached in the limit of a large multi-way system. Okay, where does the angle appear for the first time? For any given foliation, defining coordinates of some kind. So that means within the foliation, which it can be assigned a position in a multi-way space. In the standard formalism of quantum mechanics, states are thought of as vectors in a Hilbert space. And now these vectors can be made explicit as corresponding to positions in the multi-way space. Cool. So what we're saying is that each position or each node is a state of the system. But now there's an additional issue. The multi-way system should represent not just all possible states, but also all possible paths leading to states. And this means that we must assign to states a weight that reflects the number of possible paths that can lead to them. In effect, okay. Now so we're getting to the angle stuff, I think, at some point. So let us say we're going to track what happens to some part of this branch-like hypersurface. Each state undergoes updating events represented by edges in the multi-way graph, and in general, the paths followed in the multi-way graph can be thought of geodesics in multi-way space. Paths followed in the multi-way graph, geodesics in multi-way space. And to determine what happens to some part of the branch-like hypersurfaces, we must then follow a bundle of geodesics. What happens to some part of the branch-like? Yeah, okay. So we follow a subset of the evolution. A notable feature of the multi-way graph is the presence of branching and merging, and this will cause our bundle of geodesics to diverge and converge. Often in standard quantum formalism, we're interested in the projection of one quantum state on another. In our set, the only truly meaningful computation is of the propagation of the geodesic bundle. But as an approximation to these that should be satisfactory in an appropriate limit, we can use distance between states in multi-way space, and computing these in terms of vectors. I don't know. Let's keep that. Time evolution. Okay, so time evolution in our system is effectively the propagation of geodesics through the multi-way graph. And to work out a transition amplitude between initial and final states, we need to see what happens to a bundle of geodesics that correspond to the initial state as they propagate through the multi-way graph. We want to know the measure of the geodesic bundle when it intersects the branch-like hypersurface defined by a certain quantum observation frame to detect the final state. I think what all that means is you have a foliation where your target state is, and you want to somewhat measure what are all the paths going, like how they're going to cut through that foliation. To analyze this, consider a single path in the multi-way system corresponding to a single geodesic. The critical observation is that this path is effectively turned in multi-way space every time a branching event occurs, essentially just like in the simple example below. So the path has a series of turns. If we think of the turns as being through an angle theta, okay, but is this angle referring to each turn? Yeah. The way the trajectory projects into the final branch-like hypersurface can... okay, so this is probably what we need to unpack. The way the trajectory projects onto the final branch-like hypersurface can be then represented by okay, so what's the branch-like hypersurface here? How is this defined? Okay, so the branch-like hypersurface is the actual observation frame. So I'm trying to visually think about these, right? And if you think about that observation frame, for example, being the last, so that foliation being like the last level in here, the projection of the geodesic, it's like, right, like you would have that projecting. So you have an angle theta. But I don't know if the angle theta is something that you defined at the geodesic level. So you're saying, assuming that's your reference point, then you have this path like these, and so this is where it ends up projected, right? And so there's an angle here. From that point to that point, you can draw a line and say, well, there's the geodesic has an angle here, an angle with respect to like a projection of this state onto this one, which I don't know if that makes sense at all or not. And so the way this projects is this. But the thing is, I mathematically don't understand what this means, right? So I think I need to understand it a bit more about what it means to raise the exponential to a complex number times these. To work out the angle theta for a given path, yeah, okay, so that's at the path level. We need to know how much branching there will be in the region of the multi-way graph through which it passes. But I recall discussing space-time with the flux of edges through space and causal graph is potentially corresponding to energy. Okay, so that was discussed earlier. So, okay, so the two things that I want to dig into later is like how and why is this somewhat mapped to energy? The space-time identified the flux of edges through space like hypersurfaces in the causal graph as potentially corresponding to energy. No. Okay. I mean, so this is something I could definitely go and try to take a look at back where is that then explained. There could be a reference, to be honest, but this is an important thing to keep an eye on. So this projection can be represented like this. I don't know why. Note that every node in the multi-way cascade represents some event. The amount of turning in a path is proportional to the energy multiplied by the number of steps, or effectively the time. In standard quantum formalism, energy is identified with a Hamiltonian. So what this says is that in our models, we can expect transition amplitudes to have the basic form of, so here they go ahead and replace the angle by the Hamiltonian and the time. So basically they're saying, cool, so the angle is then proportional, and then they ignore the constant here, right? So it's, yeah, they ignore any constants. It's like this angle is proportional to the energy times time. Because this is familiar. Because this is a way to think about operations in quantum mechanics. Yeah. So I need to basically try to understand how they come to these. Because then it's like, yeah, there you go. So the thing about this in more detail, we need not just a single energy quantity corresponding to an overall rate of events, but rather we want a local measure of event rate as a function of local location in multi space. Foliation, but now we can make a potential identification with standard quantum formalism. We suppose that the Lagrangian density L corresponds to the total flux in all directions, the divergence. Yeah, okay, so that starts to make a bit more sense, because now what if I understand this well, is like there's the supposition that the Lagrangian density, which I'm assuming is just the Lagrangian, corresponds to the total flux in all directions, or in other words, the divergence. If I understand this well, what this probably means is that the Lagrangian would be how much the different geodesics diverge, which kind of makes sense from a stationary action principle perspective, because if there's no flux, it means it means that the Lagrangian is at its minimum, And if there's like huge amount of flux, it means that there's a lot of action, there's a lot of stuff happening, right? Um, so it's a lot of this is a lot of supposition, right? So there's this is just a super high level, but what they're kind of I try to I think I'm understanding a bit more what they're saying, the way they're trying to map the model. So they're saying that the Lagrangian can be defined as a function, whereas at each point you take a look at the flux instead of the kinetic energy and potential energy, right? So now I can see a path and multi-way system going through multi-way space. To know how much turning to expect in the path, we need to, in effect, to integrate the Lagrangian density along the path. So you need to integrate across the different flux together with the appropriate volume element. This I don't know what it is. And this will give us something of the form where S is the action. But this is exactly what we see in the standard path. Okay. It's notable. So I think this is high level enough that I think that allowed me to close a lot of the gaps, at least at a high level. And I guess the Lagrangian density is just the Lagrangian. The only blank spot that I have here is how they come to this conclusion that the way something projects is like that, because then they go, and why is the projection important here? Because that tells you okay, because that tells you where it projects, and then if you then you can, for all the geodesics, calculate that, and then you can kind of derive the actual amplitude transition amplitude out of that, which will be in the same form, just because they're saying theta is proportional to the energy times time, which is then somewhere defined earlier in the whole model, right? Cool. It's awkward. It's awkward because it feels good. It feels like pieces fitting together, but it's like every single piece you're connecting. It's just yeah, but I mean, I guess that's just a technical introduction. So this is obviously lacking all the detail, right? Mm. Okay, but let's try to dig into these. So turns being through an angle theta, the way the trajectory projects into the final branch-like hypersurface can then be represented by. How do we go about these? So e to the power of I, of infinity, no, of I. What does it mean? Because I remember there's definitely some 3 blue, 1 brown videos about these. E to the pi I. It's an old version. Okay, so here's e to the pi, Euler's number. Imaginary exponent. So fundamentally, Euler asserts that e to the power of I times pi is equal to -1. The expression is a special case of the expression e to the power of z, where z is any complex number. In general, e to the power of z is defined for complex z by extending one of the definitions of the exponential function from real exponents to complex exponents. For example, one common definition is is the limit. Okay, so this is the limit of n tending to infinity of 1 plus. Okay, so that's the. And this animation n takes various increasing values from 1 to 100. The computation of this is displayed. Okay, so that is what this is supposed to be defined, right? It's the definition of e to an exponential power of pi, and I guess pi in this case is that's the reason why you have it like these, right? But then on top of that, here we have, okay, theta being an angle. So actually that's quite appropriate, because we still get an angle. So it's the combined effect of n repeated multiplications of the complex plane, with the final point being the actual value minus 1. Yeah. So essentially, that complex component, just what it does is infinity. I'm not so sure I grasp that. Geometrical interpretation. Any complex number can be represented by the point xy in the complex plane. This point can also be represented in polar coordinates as r and theta, where r is the absolute value of z, distance from the origin, and theta is the argument of the z angle counterclockwise. By definition of sine and cosine, this point has certain coordinates, implying that z is according to Euler's formula. This is equivalent to saying that, oh god, as a factor of the number minus 1. Its distance from the origin is 1, and its angle from the positive x-axis is pi radians. But what does this tell us about projections? Oh, kind of, I think I know where this is going, right? So I think, okay, I guess taking that animation, you could think of these, like that actually defines as some sort of geodesic with an angle, And in this case, the angle will be pi radians, right? So what e to the power of I times pi is defining is that type of geodesic, right? It's sort of like half a circle, where of course if you vary the angle, you're gonna get different paths. But how is that a projection? This is what's not totally clear yet. So how the way the trajectory projects onto the final branch-like hypersurface can be represented by why? Why is this somewhat a projection into the final branch-like hypersurface? The projection being the spot where it ends. Is that what it means? Give me a second. Sorry, it's a lot of packages coming in today, and actually running out of time anyway. But okay, but I do see some connection, at least between these animation, right, and then say kind of like trying to understand what the projection is. I don't know, think about this, maybe. But it's got to do something with the trying to define where it ends, because this is the E component of it. Exponentiated with a complex number kind of has these effect of like turning into a curve, sort of like into like a, you know, kind of like a circle kind of thing, and then theta, yeah. So maybe that's something where, like, if you want to approximate that geodesic and think of it as a something with an angle. Yeah, maybe we could play with these, but I don't know what we would do to play with it. Maybe kind of plot these as well and see where these goes. If you have this angle and how that is a trajectory. Sorry, how is that a projection? That is, I think, the next step, the next thing to figure out. But okay, so there's this whole concept here. Now, I think that now at least I understand a little bit more how they're trying to bridge these things. With the exception of this being a projection. But this means that I think I am a bit more ready to start digging into the path integral formalism, because that seems like the right way, the right next step, right? So the basic quantum mechanics concepts, the formalism, and then this, and then we can come back to measurement, the path integral, and yeah, I think I should put the Wolfram stuff aside for now and go and deep dive into the path integral and the Schrodinger's equation, because that's like, but I think that's more the operational, the operator formalism, isn't it? Or the more kind of classical way or typical way to think about quantum mechanics, the Schrodinger way. I wanted to do a bit of a kind of video session as well at some point, and basically kind of either watch or rewatch a video. And the problem is I'm not getting the sound through the speakers, through the headset while I do this. So I'll have to play with OBS a little bit and see if I can get that. Because, you know, if you guys can hear it, it's cool. But if I can't hear it, then I can't watch a video. Path integral. What do we have here? What a path integral problem looks like in quantum mechanics. Maybe that would be one. Yeah, I think that could be one to watch, because it's less of a that's the general introduction, blah blah, just taking a look at what a problem looks like. That could be the one to watch, and it's how long?
Oh nein, wurde dein Spiel gerade von einem Update?
Let me spare you the ad. And so this is 5 minutes. Oh, that's really short. Okay.
Because in certain cases.
Okay, but let's do that. I'll try to figure out how can I get the audio through my headset as well as you guys hearing it from the OBS recording, and then see if so we'll do that. So we'll take a look at path integrals next time. Now, at least I feel I've kind of closed most of the gaps in between the way this is trying to be. They're trying to model these, but now let's get into the path integral stuff a bit more, and then we'll see how can we derive the Schrodinger stuff from that perspective. And then yeah, maybe once I got a bit of a bird's eye view on these, it's time to kind of get going with some problems. I feel like just floating around the theory, it's good, but it does not really stick together, or stick in my brain unless I get my hands on with an exercise. So, and then we can try to play with the model a bit more afterwards. We'll see where that goes. But that feels like the right thing to do. Awesome. See you next time.